So I've known Britton for about 26 years. I met him at the University of Illinois. He was a graduate student studying under Dale van Harlingen, and he did a number of very interesting studies on fluxons. After that, he went to Cal Berkeley, where he did a postdoc with John Clark, and he eventually settled as a professor at Syracuse University, where he's done a number of very interesting works. You're going to hear about that today, but I want to mention also two of his interesting activities at Syracuse University. He was editor-in-chief of IEEE Transactions on Applied Superconductivity for 6 years, which is a huge commitment. That's a journal that publishes a number of very important on a number of important devices in superconducting circuits. And then also he became an IEEE fellow just last year. So without further ado, here we go. Thanks.
Okay, well, thank you, Kevin, and thanks everyone for coming today. It's great to see you all. It's been a little while since I've been down to College Park, but I always have a fun time coming here and seeing old friends, meeting new people, and yeah, talking science. So I'm going to tell you today about some work in my lab at Syracuse University and in my collaborators' lab, Robert McDermott's group at, get used to this soon, at the University of Wisconsin-Madison, looking at superconducting qubits and coming up with ways to protect them from environmental poisoning. We'll talk as we go through the slides about what we mean by environmental poisoning. But basically, the theme of the talk today is going to be quasiparticles in superconductors and what they are and what issues they cause with trying to operate high coherence superconducting qubits. Okay, so let's start out by just having a brief overview of the past 2 decades of the developments in the field of superconducting qubits. And so superconducting qubits, of course, one way to build the elements of a quantum computer. And they've enjoyed this really incredible rise in coherence over the past 2 decades. This is plotting lifetime. Take your pick if you want to think about T1 versus T2. But starting back in, I'll get used to it soon. Come on. Yeah, maybe that's actually easier.
Yeah, it's so small.
Yeah, you can see that, right? Let's do that. We'll do that. So starting back at the, where'd it go? Yeah. I'll gesture, how about? So back in 1999, the very first superconducting qubit was made in Japan, in NEC. It was great, tour de force, it worked, everybody was super excited, but the coherence time was a nanosecond or a couple nanoseconds. Not super useful, but over the past 20 years or so, there have been all sorts of developments and improvements in designs of superconducting qubits, shielding, filtering, and improvements in materials that have all led to these sort of 5 orders of magnitude improvement in coherence times. This is a log scale here. And this is already several years out of date. This is from a review article from the MIT group back in 2019. So it's this sort of Moore's law improvement in coherence. So now that state-of-the-art coherence times are beyond 100 microseconds. And that's important because relative to the gate time for doing gate rotations of superconducting qubits, that's quite large. Gates are typically in the tens of nanosecond type of regime. So that's led us to this noisy intermediate scale quantum regime, the NISQ era. And it's meant that these coherence times are good enough to start doing initial steps towards quantum error correction. And it's also meant that some of the big players like IBM and Google can make pretty large scale quantum processors. So I believe this is the latest IBM. I think it's their Hummingbird. No, sorry, this is the last one. I think was the Hummingbird. This is the Osprey. They seem to have a bird theme going. And the Osprey one, I think it's 433 qubits. It looks like a big silver rectangle, but behind that, I guess, are 433 qubits. And the Google Sycamore system that they've been working on for several years, that they did their quantum supremacy demonstration with, that system had 53 qubits. But the point is, it's already possible to build these pretty large scale systems. They're still a long way away from universal quantum computers. And one of the big things that needs to happen is these coherence times need to get even longer. And we need to get even better gate fidelities. So there's still this never-ending quest for more coherence and understanding what limits the performance of qubits. But another piece that's been realized just in the last couple of years, that besides just needing individual qubits to be better, we also need to understand correlated errors. So when multiple qubits or all qubits on the chip have an error at the same time, that's a bit of a different problem. That's an even bigger problem from the standpoint of trying to implement quantum error correction. Basically, large-scale correlated errors break quantum error correction, at least the quantum error correction schemes that we know about nowadays. So we're going to be talking about both of these things and how they're connected to quasiparticles. But just before we do that, let's have just one slide about how a superconducting qubit works, just since maybe not everybody in the audience is an expert in superconducting qubits. And so we're going to be working with more or less the simplest garden variety qubit that's been the workhorse for many years in the field, which is the transmon qubit. Although the experiments we're going to be doing, we're going to make a slight tweak to the transmon. But the basic idea is we need a nonlinear oscillator to be our two-level system that's going to be the qubit. We want it to be very high Q. We want it to have a really long lifetime. And so with superconducting circuits, there's a very natural way to make a nonlinear element, namely a Josephson junction that's formed from taking two superconducting electrodes, bringing them very close together and separating them by a thin sort of nanometer scale tunnel barrier. And with these small Josephson junctions, one of the most reliable ways to do this, that's what just about everyone in the community does, is use aluminum for the superconducting electrode. So this is a picture of one of our typical junctions where these are aluminum electrodes here on a silicon substrate, and the insulating barrier is a thin nanometer scale aluminum oxide layer. And so if we do that, this Josephson junction inductor is an inductor whose inductance, given by this equation here, depends on the amount of current going through it. So that's the nonlinearity we need to make a two-level system. And so we're going to take sort of the simplest possible electrical engineer's picture of a qubit, an LC oscillator, and just replace the L with the Josephson junction. So now we get this nonlinear LC oscillator. And if you were to quantize this, you would get this level spectrum with unique spacings between, say, the ground and the first excited state and the spacings to all the higher levels. This is out of a really nice review article also from the MIT group from several years ago. That's, I believe, like the Quantum Engineer's Guide to Superconducting Qubits, something like that. And so our qubit states, the 0 and 1, are going to be these two lowest levels in this anharmonic potential. Okay, and in practice, what this looks like is shown down here. This is one of our typical qubits. The lighter shade, the light gray is superconducting metal. And the black region is where the metal's been etched away, and you're seeing the substrate. And the Josephson junction is too small to see in this picture, so it's highlighted here by this yellow bar down at the bottom. And this plus sign, this superconducting plus sign, the shunt capacitance is the capacitance from that plus sign to the ground plane that's all surrounded all around here. And the typical parameters are shown over here for if you want to know about how big the capacitances and junctions are. But the key thing to remember is that the typical transition frequencies, so the spacing between these 0 and 1 states of the qubit over here, is in the ballpark of 5 gigahertz or so. And the anharmonicity is small, but big enough. So few hundred megahertz or so is typical. Okay, so what are the main sources of decoherence in these systems? So just like any qubit, we can represent its state on the Bloch sphere. And we have our north pole, the 0 state, south pole, the 1 state. And the goal is to be able to prepare arbitrary superpositions of this circuit. And just to make sure we're all speaking the same language, I'm sure we already are, but just we can break these decohering processes into two categories. There's T1-like processes that relax an excitation back to the ground state. And then there can be dephasing processes that cause a superposition to dephase. And so the first gives us bit flip errors. The second gives us phase flip errors. And we can look at some of the bad actors. What are the biggest causes of these two types of processes? And in the case of dephasing, it's generally in any type of fluctuation in the circuit that causes that 0-1 splitting of the qubit to wiggle up and down in time. That will cause a superposition to dephase. So that can come from things like flux noise. If the qubit happens to be sensitive to flux, it can come from charge noise. If the qubit happens to be sensitive to charge, it can come from fluctuations in the photons in the microwave readout resonator that's used to measure the qubit. It can also come from fluctuations in quasiparticles, which we'll be talking more about in the next few slides. But on the relaxation side, kind of the biggest thing is dielectric loss, which we're not going to talk about today. But understanding dielectric loss and trying to mitigate it has been one of the big drivers that's pushed qubit coherence upwards over the past 20 years or so. But the one we are going to focus on is the idea of, that should be one more down. circle around both of them. Non-equilibrium quasiparticles. And so that's going to be our sort of our focus for today. And so, what is a quasiparticle? Well, what is a superconductor? So, a superconductor is a superconductor, DC zero resistance of electrical current. And the superconducting state is characterized by Cooper pairs that are condensed into a ground state at zero energy. All right, there we go. At the Fermi energy. And okay, so our Cooper pairs are living down in this, they're condensed into this macroscopic ground state with macroscopic phase coherence. But, and then there's a gap to single particle excitations of delta. So this capital delta is our characteristic energy scale of the superconductor. And it's going to be in the ballpark of, say, 100 micro electron volts up to milli-electron volt or so. So that's the energy scale to have in mind. So hundreds of micro EV up to milli EV. And if you somehow have energy around in the qubits environment that's in that range or higher, it can break a Cooper pair. And that energy could be absorbed, say, as a phonon hitting the superconducting film, or a photon hitting the superconducting film. Either of those mechanisms will break a Cooper pair and generate two quasiparticles. It'll be able to, if that energy is above twice this energy scale, 2 delta, it'll generate two quasiparticles above this single particle excitation gap. And that's problematic because quasiparticles dissipate. They do carry entropy, unlike the Cooper pairs in the ground state. And so if you have quasiparticles running around your superconductor, that's bad. That can limit the qubit lifetime, can also cause dephasing. Now, when you have quasiparticles up at high energies, they can scatter inelastically off of phonons in the superconducting lattice, but they can't scatter any lower than delta, right? They can scatter down to this delta, where there's this peak in the density of states, which I realize now I should have said earlier. We're looking at the density of states in the superconductor and energy on the vertical axis. But once they scatter down to the gap edge, down to delta, they get stuck there. But if there's enough quasiparticles hanging around, then two quasiparticles can actually find each other, what we're showing over here, and they can actually recombine and form a Cooper pair and drop back down into the superconducting ground state. When that happens, the system actually emits 2 delta of energy, most generally as a phonon that gets kicked out. Okay, so we're going to be thinking about both of these processes throughout the talk today.
Now, it sounds like what you're saying is that these quasiparticles, you start with Cooper pair,
yep,
right? And the quasiparticles, the way you've drawn it, looks like two unpaired electrons, which then could recombine to form another Cooper pair.
That's right.
Why do you call them quasiparticles? They sound an awful lot like particles.
Yes, so because they're excitations above this ground state, they're still dressed by the condensate that they're living above. And a quasiparticle, it's strictly speaking, it's actually a superposition of an electron in a hole. And they have all sorts of strange properties that you don't have with just say a single electron or a single hole. Namely, one weird thing is when you're up at high energies, far above delta, the diffusion constant of the quasiparticles is relatively large. They can kind of zip around the superconductor, but as they scatter, say inelastically off of phonons and drop down towards delta, their diffusion constant goes to 0. So once they get to delta, they're effectively stuck in their place. They can't diffuse around, and they just wait until another quasiparticle is close by, and then they can recombine.
Okay, but I'm not seeing the hole here. Where did the hole come in this picture you're showing?
This is an oversimplification, so I didn't want to get too far into the weeds of quasiparticle dynamics. And I didn't make any backup slides to sort of go through the details. So it might be a thing to chat about, maybe if you want to bring it up at the end. But for what we need to talk about today, this will be sort of the picture of thinking about these quasiparticles that kind of behave like single electrons, but they're not quite single electrons. Okay, but let's still talk a little bit more about them here. How can you make quasiparticles? We talked about two mechanisms. You can zap the superconductor with a phonon above 2 delta, or you can zap it with a photon above 2 delta and break a pair and make quasiparticles. You could also make quasiparticles just by raising the temperature. Okay, so one of the typical ways we characterize the quasiparticle density is up here. We could think about the volume density of quasiparticles relative to the volume density of Cooper pairs here. So we get this dimensionless quantity that says how many quasiparticles we have to how many Cooper pairs we have. And if we want to try to make quasiparticles just by changing the temperature, this is the expression here to look at. And it's got this exponential in it, which you would imagine is going to really suppress the density of the quasiparticles if we cool the superconductor down. And just to put some numbers on it, for aluminum, this gap is 2 Kelvin. And okay, if we were to operate on a dilution refrigerator, which we normally do for our qubit experiments, down in sort of the 10 or 20 millikelvin range, you can calculate how many thermal quasiparticles we should have, and it's a ridiculously small number, 10 to the minus 50. Just to put a scale on that, if that sounds like a very small number, probably to everyone here, but if you wanted to think how big of a superconductor do you need to get a pair of quasiparticles at this temperature, you need a solid sphere of aluminum at 10 or 20, I think this calculation was for say 15 millikelvin. It would need to be larger than the volume of the Earth. I think it's almost about the size of Jupiter to get one pair of quasiparticles generated thermally. So there basically aren't any. Yeah, I don't know where you'd get that much aluminum in the first place. But surprisingly, experimentally, over the years, people have known about this for more than a decade now. When you really try to carefully measure how many quasiparticles are in your superconductor at 10 or 15 millikelvin, you get a whole lot more than 10 to the minus 50. People typically find something in the range of, say, a little less than part per billion up to part per million type levels without doing anything intentionally, without trying to generate quasiparticles. And so that's a big discrepancy, right? 40 orders of magnitude is something we ought to try to understand. So something's lurking. And what could that be? Well, what that could be is most of the rest of the talk. You could have, say, the phonon parabraking mechanism, where phonons could be bombarding the superconducting film. In this case, there's a very interesting mechanism where high energy particles, like things like cosmic ray muons or gamma rays generated from background radioactivity, can generate bursts of high energy phonons that can break pairs in a superconductor and generate quasiparticles. But you can also have this photon-mediated mechanism where, say, if you have stray high energy photons, say millimeter waves or even terahertz level photons in the qubit environment, say from black body radiation from hotter parts of the refrigerator cryostat, those can get absorbed in the film and break pairs, generate quasiparticles. There's also a relatively recently uncovered mechanism, which is the possibility of resonantly absorbing these sort of millimeter wave photons by the qubit, by spurious modes of the qubits that we don't want to be there, but happen to be there. They come along for the ride, that can also generate quasiparticles. And that's what we're going to start out talking about, this third one. And then I probably should have written these in the opposite order. We're going to come back then in the later part of the talk to talk about the phonon mechanism. Yeah, question back.
I think radiating photons is down to the same equilibrium temperature shouldn't happen. Should I think about this as your superconductor coming into equilibrium with something far away, hot, and radiating?
Yes, so we'd like to have the qubits environment be fully at 10 or so millikelvin. That's very hard to do. So, the refrigerator works in stages. There's, the top plate of it's at room temperature, then there's a part that's at 50 Kelvin, then a part that's at 3 Kelvin, a part that's at 0.7, and so on. And so each of those stages, even the part at 0.7 Kelvin, is still a black body, and it still radiates photons at a characteristic temperature of 0.7 Kelvin, and those are extremely hot compared to the qubit. And so if we don't perfectly shield out those stray photons, they'll get into the qubit environment, and it only takes a few to then start breaking pairs. So that's the challenge, is how light tight can we make the qubit enclosure?
But the third one, the resonant thing.
Yes.
Is that resonant to these rogue photons or resonant to black body at the Dilfridge temperature?
It's sort of, we're agnostic to where they come from, but it's, yeah, as long as there are photons in the sort of millimeter wave, so hundreds of gigahertz range, they can be absorbed by this spurious mechanism that we'll talk about over the next few slides.
Okay, but hundreds of gigahertz is well above the Dilfridge temperature. Well, I mean,
yes.
It's always a tail.
Yep. But the key is if you have like a really small population of them, maybe there's not going to be enough to break pairs in the bulk of the film, but through this resonant absorption mechanism, it can enhance them and break pairs right at the qubit junction where they do the most harm. Okay, so that's sort of it for the general intro to quasiparticles. But let's now move on to talk about this this mechanism, this idea of resonant absorption. And so this came about from some really nice insight from my collaborator at Wisconsin, Robert McDermott. They had this preprint just a couple years ago that qubits, okay, we designed them to be these simplest possible LC oscillators, nonlinear LC oscillators in the 5 gigahertz or so range. But unintentionally, they also host spurious modes, and they act like antennas up in the millimeter wave range, up at hundreds of gigahertz. And what's the idea? Well, so we talked before about our standard looking qubit, which is a superconducting metal patch, like this gray plus sign, embedded in a superconducting ground plane. Okay, and it's the capacitance from that patch to the ground that gives us our shunt capacitance that we need to get an oscillator at 5 gigahertz or so. But if we simplify this, take the spherical cow approximation, and we draw our qubit island, say, as just this circular disk. So now we've gone to dark gray is metal, and white is metal etched away, where we're looking down at the substrate. So it's this metal disk embedded in a circular aperture in the ground plane. Well, this thing looks like an antenna, a patch antenna that can be driven by an electric field. And through something called Babinet's principle, this can be mapped to its dual of a wire loop antenna, where dark gray is still metal. And so it's now a wire loop antenna driven by a current source. And it's going to have a fundamental antenna resonance where it can radiate into free space. That's going to be given by just that perimeter distance around that loop. Okay, and if you work out the numbers for the size of a qubit and the dielectric constant of the silicon substrate it's sitting on, all these things, that resonance works out to be in the range of, say, 100 up to maybe 300 or 400 gigahertz, depending on the exact details, the dimension of your qubit. So way, way, way outside of the range where we're trying to design our qubit to be an LC oscillator. And it's really, until this point, it wasn't anything anyone had on their radar screen. But here, what's worse, okay, there's this spurious resonance, but what does it actually do for the qubit? Well, it turns out you can think about this in this sort of antenna receiver antenna type of picture. So we can model our junction in terms of just its normal state resistance. So the resistance the junction would have if it's not in the superconducting state through that tunnel barrier. And I didn't mention earlier, but the junction itself has an intrinsic capacitance, right? It's two superconducting electrodes separated by a thin tunnel barrier, so it also acts like a capacitor. So this sort of is the crude model of the junction. And then the question is, how well is it matched to this antenna impedance that's coupling to free space up above the chip? And well, you can think about that just in the usual electrical engineer's picture of this this reflection coefficient here, just given by the differences of the impedances over the sum of the impedances. And I should mention that this Z-rad, this radiation impedance, is something you have to calculate numerically. There's no simple, quick way you could just do it pen and paper. You have to run it through a finite element solver that basically solves Maxwell's equations and looks up over the frequency range you care about. But once you can do that, then you can calculate this, and you can calculate a coupling efficiency. How efficiently do these radiation up in free space above the chip couple to the Josephson junction? And it turns out pretty efficiently. This is not such a small number, which is a problem. So it means that we can absorb, if there are millimeter wave photons hanging around in the qubit environment, this spurious antenna mode can pick them up very efficiently and drive large currents through the Josephson junction very effectively. And those large currents are at frequencies larger than the superconducting gap. So I didn't say this before, but I probably should have. The 2 delta for aluminum, if you translate from EVs to gigahertz, is around 100 gigahertz or so. So if you've got photons above 100 gigahertz and they're getting efficiently picked up by this antenna mechanism, that's bad. It's going to make a lot of quasiparticles right at the junction where they're going to cause the most problems from the standpoint of qubit coherence.
Now, the model that you've given us here seems to be ignoring the Josephson junction.
Yep.
So what does that do?
So yeah, in this case, because we're absorbing energy above the gap anyway, the things that matter are this normal state resistance of the junction and its intrinsic capacitance. So its inductance in this case doesn't play a role when we're already irradiating it with energy way beyond 2 delta. So to capture the physics, we really just need to worry about its tunneling resistance and its intrinsic capacitance.
So the narrow bandedness of the transmon doesn't help you out here.
Right. Although we're going to actually, on the next slide, flip it around as a way to actually study this effect and use another junction where we will sort of use the fact that the Josephson junction itself can act as a coherent emitter of millimeter wave radiation. So the experiment that was done in Madison, but in collaboration with us and using some devices from my lab in Syracuse, is the following. So we tried to preserve I tried to preserve the colors from the previous slide. So we're going to still have this qubit down here that's going to have this efficient coupling to millimeter wave radiation represented in blue. And that's going to be a chip that's going to sit in this bottom sample box here. So our qubit chips are typically, in this experiment, they were 8 millimeters on a side. But then we're going to use another source of millimeter wave radiation that we can actually control, because we're talking about hundreds of gigahertz. It's not something we can just run down a simple coax line and have a signal generator in the lab. It's hard to deal with. But we realized it in lead up to these experiments that we could actually generate millimeter wave radiation coherently using another Josephson junction. So we actually use another qubit chip, although we're not using the qubits in this red one up here. We're using actually just some test junctions that happen to be sitting on the chip that we typically use just to characterize our fabrication process. We hook a lead directly up to the junction, and we can actually bias it. We can voltage bias it, which in this picture, we're going to do the Norton equivalent to think of it as a current source. But again, it's got some intrinsic capacitance. It's got a normal state tunnel resistance. And it's also got some radiation resistance, radiation impedance, coupling it to free space. And with the Josephson junction, we're going to be able to emit Josephson radiation at a frequency that we choose by the voltage that we bias it with. And then we're going to deliver that to our qubit, which is down here at the bottom, and study the poisoning of that qubit by these millimeter waves. And so we've got this sample box where we can have this transmitter junction up here at the top in red. Think of it as hot. And then our qubit that we'd like to be cold in blue down here at the bottom, that's going to be the absorber of these. So they're both in the same sample enclosure. And we're going to do this sort of pump type of experiment with broadcasting millimeter wave radiation. And the way that works, if you haven't before seen the Josephson relation, and this is the principle of how the voltage standard at NIST is maintained, is that with a voltage biased Josephson junction, it'll undergo phase oscillations in the phase difference across the Josephson junction at an extremely well-defined frequency that's just given by fundamental constants, the flux quantum phi naught, which is Planck's constant over 2 electron charges. So if you bias a junction at 1 millivolt, you get radiation, you get the phase evolving at 484 gigahertz. And if you bias it at half a millivolt, you get half of that frequency, and you can choose the frequency you emit by just the voltage you bias it with. So this is the picture. This is one of our, as I mentioned, a test junction just coming along normally for the ride on the chip. But because it's got leads to it, we can actually hook it up to a coax line. And we're going to voltage bias it up here. And we're going to ground the other pad of it. And now we've got this circuit that we can use to emit millimeter wave radiation controllably in the qubit environment all the way up to 500 or so gigahertz, which is pretty neat. We don't have to run these signals all the way down, generate them in the lab and run them down into the fridge. We can generate them right in the fridge, right next to the qubit. Okay, and what are we going to use the qubit for? You know, we somehow have to use the qubit now as a receiver, and we have to detect this poisoning process. And the way we're going to measure whether or not the qubit has absorbed quasiparticles and gotten poisoned and is through the following technique. And this is something that we're going to come back to throughout the rest of the talk as a way to characterize quasiparticle poisoning of a superconductor. So we want to know, are there excess quasiparticles on the qubit island? And one of the things that I mentioned when we had our one slide about how a transmon works, typically a transmon is made in such a regime so that it's insensitive to the offset charge in the qubit environment. So you can't tune its frequency between its 0 and 1 transition with an offset charge. And that's the way IBM and Google would make their transmon for their large hundreds of qubit processors. We're going to relax that assumption and intentionally make somewhat bad transmons. We're going to back off on the shunt capacitor parameters so that the qubit does become a little bit sensitive to offset charge of order a megahertz or so. And what do we mean by that? So now, if we have an electrode, say a gate electrode on our chip, that we can sweep a voltage bias on, with that gate electrode being very weakly coupled to the qubit island, usually maybe 50 or 100 attofarads, then we can tune the offset charge on the qubit, and we can get these periodic energy bands. So say this red one down here, if we tune it, its energy band between the 0 and 1 transition will actually tune in a way that's periodic in 2 electron charges. So in a Cooper pair, so that red curve there, we're just looking at a part of it here. But now if somehow one quasiparticle gets onto the superconducting island, then instead of an even number of charges on the island, we now have an odd number of charges on the island. And because quasiparticles are discrete, you don't have like 2/3 of a quasiparticle jump onto the island. You now get another band, this blue one, that's shifted by 1e. Okay, so that one would be for an odd number of quasiparticles or total charges on the island. One would be for an even number on the island. And if we happen to be biasing, say, right at these degeneracy points, okay, you can't tell the difference. The qubit frequency, transition frequency is the same. Whereas if you bias at, say, 0 or at 1e, then now you get this maximum separation between the even and odd parity bands that, again, it's going to be, say, in the range of 1 megahertz to up about 5 megahertz or so for that peak-to-peak difference, whether you're on the even or odd parity. So now how can we, what can we do to try to figure out which of these parity bands we're on? Well, this was a sequence that was developed actually about 10 years ago in this really nice experiment from Delft, from the DiCarlo group. And the idea is the following. If we initialize our qubit into, say, the ground state up here, and let's say we're right at this point of maximum charge dispersion, if we do a fast, hard pi/2 pulse, so that's sufficiently broadband that we're addressing both of these parity bands, then we can tip ourselves down to the equator down here. But now once we're at the equator, and we're going to do that at the mean frequency. So at the frequency right here, so right in between these two bands. So we're going to rotate them both down to the equator. But now if we're in the blue band, we're going to process faster on this side of the Bloch sphere in the rotating frame. And if we're in the other parity band, we're going to be processing more slowly on the other side in the red parity band. And so if we wait for a quarter of a period, and then now we apply a second pi/2 pulse, but this second time we do it about the y-axis instead of the x-axis, then we're going to rotate. The blue one's going to go down to the south pole to the 1 state, and the red one's going to go up to the north pole to the 0 state. So we've mapped parity of the qubit onto 1 state occupation. And then we just do a measurement. Is it in the 0? Is it in the 1 state? And we're just going to do this sequence repeatedly. And we can choose the period. Sometimes we go as fast as maybe a 50 microsecond period if the poisoning is really quick. Or we can slow it down if things are really quiet and the poisoning is slow. We can go as slow as, say, 20 milliseconds. And then after each time, we're going to get a 0 or a 1. And so we're just going to get this bit string of 0s and 1s. And each time it changes from a 0 or 1 or back from a 1 to a 0, that corresponds to a parity switch of this charge parity on the qubit island. And we can take that bit string and just compute the power spectrum from it. And in general, for this type of quasi-particle poisoning process, it's going to be something that's characterized by a simple Lorentzian knee and then a white noise floor out here at high frequencies. And it can be fit by this function here, where this gamma p parameter is going to characterize how fast the quasi-particles parity is switching. So how many quasi-particles are around. If we have lots of quasi-particle poisoning, this gamma p will be a high rate. And if things are really quiet, gamma p will be a really small number. And then just from the experimental fact that we don't have 100% readout fidelity, that's going to set our white noise floor out here at high frequencies. Okay, so that's the measurement technique we'll be using to characterize the quasi-particle poisoning. Okay, and now what does this look like? Well, so we talked earlier about the geometry. We've got this transmitter junction on top that we're going to bias up and use it to broadcast millimeter waves. And we've got a receiver qubit on the bottom that we're going to be doing this quasi-particle parity switching measurement on continuously, well repeatedly at this periodic rate. And what we can do is measure this poisoning rate, the gamma p here, as a function of the frequency of the Josephson radiation we're emitting from this top junction. And so let me first talk about this upper plot. The upper plot is some numerics. Remember, I mentioned that to figure out this radiation impedance, we have to do it numerically. So that the red curve on top is this radiation impedance as a function of frequency for the transmitter junction. So you see it's got some peaks and a little bit of structure to it. The blue curve is then the radiation impedance as a function of frequency for the qubit, for this spurious antenna mode of the qubit. You can see it also has peaks and wiggles. And then the purple curve is essentially the product of those two, right? Because that's going to tell us the coupling efficiency for how effectively Josephson radiation we broadcast from the top transmitter junction gets absorbed by the qubit down at the bottom. And the experiment we do, again, we're measuring this poisoning rate, gamma p, as a function of the transmitter frequency, which again, we set just by changing the voltage that we're biasing the junction at. And each black point corresponds to one of those broadcasting frequencies, and us measuring this gamma p. And then the purple is the same purple curve that's up here with just one fit parameter, which is a overall scale factor to account for just photon loss in the sample package. And you can see it actually matches pretty well, even doing a reasonable job of capturing this fine structure, these wiggles that are on here, which turn out are due to another spurious mechanism, which is a coupling between the qubit and an unintentional slot line mode in the qubit resonator that's around 11 gigahertz that gives this 11 gigahertz spacing. But you can see we capture most of the features that come out from this basic model. So this is sort of a validation that this picture of absorption by millimeter waves really happens, and it's really there, and we can really see it pretty quantitatively. And so as a next step, we did some experiments, in this case with some devices that were fabricated in Madison, but looking at the same idea of having a transmitter junction up on the top and a chip with qubits on the bottom. But now the experiment is to look at qubits that have different antenna frequencies. So these are all on the same chip, but this one's very compact, so it should have a very high antenna frequency. This one's really big, so it should have a really low antenna frequency, and this one's right in between. And we've switched here from plus style capacitors over to disk style. Nothing fundamental, but just a little bit easier to picture. And on the left, you can see the numerically calculated resonances. So the coupling efficiency of each of these elements to free space. And so the red one up here, the big one, the big qubit has the lowest frequency resonance, just above 100 gigahertz. The intermediate one is the black one right here. So it's in between around 200, and the little one has its peak out around 300 gigahertz, okay? And so then the experiment, though, is basically the same as what we just saw. We're going to vary the bias to our transmitter junction, sweep through that, and look at the structure in this quasi-particle parity switching rate for each of the qubits. And you can see the biggest qubit that has the low frequency resonance has a peak in this parity switching rate down around where its resonance was calculated, around 100 gigahertz. That pushes higher for the intermediate sized qubit. And the smallest qubit has its peak out much further, out around 300 gigahertz. So okay, it's not a perfect match, as not quite as nice agreement as it was on the previous slide, but the trend is definitely there. But the other thing you might notice, if we're biasing our junction so that its broadcasting frequency is below 100 gigahertz, well, we're not broadcasting pair-breaking photons anymore, but we can look at what happens to the parity switching levels, and we can see, okay, the big qubit down here, it's a lot higher than the other qubits, and the small one is a lot, almost 2 orders of magnitude lower. That's the background poisoning, just due to photons that we're not generating, that we don't want to generate, at least maybe we are, but not intentionally. They're photons that are in the qubit environment, and it's the same environment because the qubits are all sitting on one chip, but we can see we get this much lower background poisoning rate for the small qubit. Okay, suggesting a path to making qubits that, one pathway is, okay, just do the best job possible to shield your qubits environment from black body radiation from hotter parts of the fridge, but we're all human, we can only do so much. So at the other side of the coin is you can try to make your qubits very compact to push up this antenna frequency as high as possible. And you can get to lower background rates. Now, those of you that have worked on superconducting qubits before know that's maybe not such a good idea from other standpoints. From the other big contributor to T1, relaxation processes in qubits, is set by dielectric loss. And making the qubit very compact and tiny is not such a good idea for making the qubit immune to dielectric loss. So those two things are in tension, and that's something that has to be sorted out. Okay, so yeah, question.
There's also
There's not a simple explanation, but thank you for bringing that up. So when we get up around close to 500 gigahertz or so, this simple picture of the Josephson radiation emitted by the transmitter junction starts to break down because the quasiparticle density in the transmitter junction gets very high. And you actually have quasiparticles that are now diffusing out into leads, and you get now much more complicated incoherent emission process. So we're sort of limited in how much we can do up here. And you'll notice actually on the previous slide, I didn't draw your attention to it, but okay, things agree pretty well up until right around 500. They don't agree at all anymore because the simple antenna model picture would predict we should have just about no coupling up at this point, but we clearly get this uptick here. And that's due to this more complex sort of incoherent emission, just from this approach to using this transmitter junction to broadcast the radiation. Yeah. Yeah, I mean, just because once we know that once we got beyond this regime, we're not really capturing the physics anymore, and so we don't. There's no our model breaks down, I guess, and I mean there's no fundamental reason we couldn't just bias it out further. Sure. Okay. Yep. It just gets further and further outside of the regime we understand. Yeah.
So your model had a background, and you said it had a Lorentzian. Is the main Lorentzian, the main peak we see here, supposed to be thought of as the Lorentzian of your model? Or
not quite. So yeah, well, so the Lorentzian, each point it comes from the Lorentzian. So basically each point on that graph is a measurement of this entire power spectrum and the fit. So the Lorentzian has a characteristic knee frequency given by this gamma p. And so at each point on that curve, each black dot represents a measurement of this string of parity switches, typically tens of thousands of these. And then we compute the power spectrum from it, and we get the knee frequency. And so the idea is, as we sweep along the transmitter frequency, this knee frequency changes by a lot, right? It goes from down here, and it reaches a peak as high as this when our transmitter is tuned right to this biggest spurious antenna resonance of the qubit. And so the parity starts switching a whole lot faster when we're on there, and then we go past it, and it comes back down again.
Looking at the inset, the extra peaks seem to be well represented on the right-hand side and sort of 180 degrees out of phase on the left-hand side, sort of suggesting that some parameter needs to be adjusted. What's going on?
I mean, we don't know exact details yet. I mean, there's all sorts of, like I mentioned, the spacing between the fine structure is right about where this slot line mode would predict it to be. They're split by just about 11 gigahertz. The exact details of it are a little trickier to think about. Like, is there some, the model assumes there's no polarization dependent, that the emission is coherent from this transmitter junction, but it's scattering off of the boundaries of the sample package and getting mostly randomized in polarization. But maybe is there some subtlety that it's maybe not perfectly unpolarized?
What I'm wondering is, what if you adjusted the size so that it wasn't the thing you actually manufactured or measured, to see if you could
yeah, or
around.
Actually, an easy way, this particular experiment didn't have, one of the things we often do is add some superconducting wire bond jumpers across the resonator to try to suppress those slot line modes. This particular experiment didn't have those on. So that's certainly one natural thing to do, is to try to add those in and see if those fine structure wiggles go away. And that's, yeah.
Data that is demonstrating this gamma p parameter without the presence of the transmitter. Do you see sort of where the resonances are from essentially background data?
Well, I mean, we can't really, right? Because this axis here, it comes from, we control the frequency we're broadcasting. So we don't really, the axis wouldn't have a meaning if we didn't have the junction. But it's a good question. So, but all we can measure is effectively this sort of zero frequency limit if we don't have the transmitter junction biased. And that's whatever we get. We don't know what the photon spectrum is inside the box for the things that we don't control directly. So let me move on to sort of the other big quasi-particle poisoning topic. So we spent a while talking about this photon-mediated poisoning from relatively high energy photons that are in the qubit environment. But let's now talk about another poisoning mechanism, which is the other side, phonon-mediated poisoning, so from lattice vibrations. And in particular, so the photon-mediated picture is something that gives us sort of excess non-equilibrium quasiparticles in the superconductor. That's something that can explain that 40 order as a magnitude discrepancy we talked about between needing a sphere of aluminum the size of Jupiter to, okay, our chips are not the size of Jupiter, to explain the typical measured quasiparticle density. That's explained by this antenna resonance spurious photon picture. But another important mechanism is this phonon-mediated poisoning, that this is problematic because it can cause correlated errors, which I mentioned are a big issue for eventually trying to run quantum error correction on a large scale processor. And so now, where can these phonons be coming from? Well, just in the last couple of years, there's been a realization that qubits can be sensitive to high energy particle impacts, in particular things like muons from cosmic rays, and also gamma rays from just background radioactivity in the lab. So if the concrete in the floor of our lab has some potassium-40 in it, which it almost surely does, or some different isotopes of uranium or thorium, those things can all emit gammas that can have enough energy to blast through the walls of the cryostat and every now and then ping the chip of our qubit. And this was studied, these two papers, just back in 2021. This was an experiment from the Google group on the left, where they looked at correlations in T1 errors across a 54 qubit array. And they could see that there were these periodic bursts that happened roughly once every 10 seconds, where a large chunk of the qubits would suddenly have their T1 drop by a lot, and then it would recover on, say, in their case, it was millisecond or tens of millisecond kind of timescales. The one on the right, which we'll focus on for the next couple of slides, was an experiment also done in Robert McDermott's group, where they were looking at correlations in charge jumps between these slightly charge sensitive qubits, also due to background radioactivity. And so let's dig into the one on the right a little bit here. So the idea is, again, to make these qubits that are slightly charge sensitive, but now instead of using that charge sensitivity as a way to measure quasiparticle charge parity, they actually use the qubits as just direct charge sensors. So to sense the offset charge in the qubit environment. And the layout had 4 different qubits, identical in size, but with different spacing. So this pair down here, they're about 300 microns apart. The pair up on the top up here is about 600 microns apart. And then, of course, you can look at pairs across the top and bottom of the chip. And what they were doing was looking simultaneously at the offset charge in the environment of each of those 4 qubits as a function of time over, in this case, 10 hours. So, setting it up, going home and having a pizza, or maybe even just running it overnight. And what you can see is there are these occasional jumps in charge, offset charge of the qubits that each qubit sees. Each color is one of the 4 qubits, should be color coded up there properly. And this sort of thing, these charge jumps have been seen for many years, going back to the very first superconducting qubits 20 years ago. But here, the idea is to look at correlations in the charge jumps. And the qubits that are close together, like say the red and purple ones, or the dark blue, light blue ones. I'm a little bit colorblind, so don't laugh if I said the colors wrong. The steps are very correlated. Like each time the purple one has a step, the red one almost certainly also has a step. They're not always in the same direction, but they very often happen at the same time. But when you get to qubits that are on opposite sides of the chip, the correlations are pretty weak. The jumps don't really happen. So something's going on there, which is interesting. But the even more interesting thing is this experiment, where they're doing the same kind of monitoring of charge jumps, but they're only doing it on one of the qubits. In this case, the blue qubit, Q1, okay, which is up here. So they're repeatedly monitoring its offset charge. And then they're going to simultaneously measure T1 on 2 of the other qubits. So Q2, the qubit right next to it, and Q4, the one all the way on the opposite side of the chip, diagonally opposite of it. Those 2 qubits, they're just going to repeatedly measure T1 on. And what they can see is that they're essentially using this charge sensing qubit as a charge trigger. So when there's a charge jump on Q1, they see a dip in T1 of those 2 qubits. So somehow the qubit up here is seeing its offset charge jump at the same time that the 2 other qubits see their T1s drop. And it recovers, in this case, faster than the Google experiment, but something like 100 microsecond or so timescale. It recovers back to the baseline T1. Now, what could be going on to explain this? And well, the picture is the following. So let's say some high energy particle, like a gamma ray or a muon, hits the chip. Okay, it's gonna get through the superconducting film, but the film is pretty thin. That's not the problem. It plows into the silicon substrate, which is a much bigger part of the volume. The substrate is typically 0.5 millimeter, 500 microns or so thick. And then with pretty high probability, these processes, like a gamma ray, typically deposits around 100 keV. Muon is a little higher, up around an capital MeV. And remember, the scale for superconductivity is a little MeV, or even a little less than that. So this huge discrepancy, many orders of magnitude difference in the energy scales. And so when that particle first hits, let's say a gamma ray, when it first hits in the silicon, it's going to generate a whole bunch of electron hole pairs. Those electron hole pairs are going to start to diffuse around, and they're going to diffuse differently based on the band structure of the silicon. That's what gives us these offset charge jumps that people see periodically. But then as those electrons and holes are diffusing around, they're also going to shed phonons. And those phonons are going to be at very high energies, much higher than the superconducting gap. And whenever those phonons, for one thing, they're going to spread throughout the whole chip. But then whenever those phonons hit the superconducting film on the top surface here, okay, cool, they'll, with high probability, break Cooper pairs and generate quasiparticles. And so this is a problem. And this is something that's really just been starting to be studied just in the last couple of years. And so sort of the final part of my talk here is an experiment we did at Syracuse to try to study this mechanism. And in particular, try to come up with ways you could try to mitigate this. So one thing you can imagine, well, if we're worried about muons, why don't we just go down in a mine shaft and use the Earth to shield ourselves from muons? So we can do that. We personally can't do that, but people have done that. There is a DR in a mine shaft at Fermilab. That's a lot of work. It's hard to get a DR in a mine shaft. But also, it turns out muons are actually less of a problem than gamma rays. And then that's a whole lot harder to get rid of all the radioactive contaminants in the lab that are going to give you the gammas. And so that's a much bigger deal to try to work around. So you can imagine maybe micromachining the silicon to try to suppress this phonon transport. And that's something we're actively working on with our collaborators in Madison. But the first thing we decided to try was coming up with a way to down convert this phonon energy and try to channel it away from the superconductor. And so the picture here was actually suggested by John Martinez recently in this paper, is to put some normal metal, essentially cooling fins, on the back side of the chip, so down here, so that whenever phonons make their way to the bottom of the chip, they can go into the copper, normal metal, we're going to use copper, and then they can scatter off of conduction electrons in the copper and scatter inelastically and essentially heat up those conduction electrons. But those conduction electrons are on the entire opposite side of the chip, so we don't really have to worry about them getting a little hot. But then when those phonons come back into the silicon, they're going to be at lower energy. And if that process happens enough, they'll be at low enough energy to be below the superconducting gap and not be problematic for the qubits. And so the experiment is this. We're going to make two sets of chips with nominally identical qubits on top, but one of them is not going to have anything on the backside of the chip. These are side views of the chip. So blue is the superconducting ground plane. Yellow is the superconductor that we make the junctions out of. So this control chip won't have anything on the backside of it, but then the other chip will have these copper islands patterned on the backside of it. And so we can wait for a gamma ray to randomly hit the chip and make a bunch of phonons and poison our qubits. Or just like before, we use tunnel junctions, like test tunnel junctions on the chip as these radiators, as transmitters of millimeter wave radiation. We can also use those same sort of extra tunnel junctions on the side of the chip as sources of phonons. So we can bias up a tunnel junction on the side of the chip up above 2 delta, make a lot of quasiparticles in the junction, and rely on this recombination mechanism. Those quasiparticles will recombine and emit phonons that can act as they can give us a way to inject phonons controllably at a given point in time and a given point in space. And those phonons can bounce over and break pairs in our qubit junctions and cause this same type of poisoning mechanism. Okay, this is what the chip looks like. We're going to focus on these 3 qubits, the ones labeled A, B, and C, and we're going to use these different tunnel junctions around the perimeter of the chip. The chip that has the copper on it, well, we're going to use this tunnel junction as our source of phonons, and the one without the copper, we're going to use this tunnel junction down here. But either way, we're going to be broadcasting now phonons throughout the chip. Okay, and the first experiment we can do is just look at the T1, the relaxation time of the qubit, as a function of this injection of phonons. And so in the experiment on the left side here, we're going to inject a pulse of phonons. So we're going to momentarily bias our junction up well above 2 delta, up to 1 millivolt for 10 microseconds. So inject a burst of phonons. And then we're going to measure T1 of both qubits with some variable delay time after the injection pulse to when we measure T1. And the color coding scheme is red is going to be the chip that is the control one, doesn't have any copper on it. Blue is going to be the chip that does have these copper phonon absorbing structures. And we're plotting the inverse relaxation time here. So 1 over T1 minus the baseline relaxation rate that we measure. And so a high number here is bad. It means the relaxation got worse. And so what we can see is as we wait after our injection pulse for the chip, the control chip with no copper, T1 gets worse and worse and worse and peaks about 30 microseconds or so after our injection pulse ends. And then it recovers as those phonons, as the chip sort of cools off and the phonons escape, and it recovers with a characteristic time of about 60 microseconds. The chip that doesn't have copper, we don't really see much at all. So the phonons don't really ever make it to the qubit. So that's already sort of a good indication. And since I'm running short on time, maybe ask me questions about the second plot if you want. But the key is there's a big difference between the chip that has the copper versus the one that doesn't have the copper. We can also do this parity measurement, this quasiparticle parity measurement, just like we did with the photon poisoning experiment. Same pulse sequence, same fits, measuring of a power spectrum. And we can see in this case, both the chip that doesn't have the copper and the chip that does have the copper actually have really low parity switching rates. The chip without the copper, this is already about the world record in sort of the lowest quasiparticle parity switching rates that have been measured, a little below a hertz. In this case, it's about 300 or so millihertz, 0.36 inverse seconds. The chip that has the copper is even another order of magnitude lower, so 0.023 inverse seconds. And so this also shows us the copper is doing something. We can look at how that switching rate changes now as we sort of periodically inject phonons, and we vary the width of our injection pulse for these phonons, which sort of controls how many phonons we're injecting, and we can measure the probability of the qubit parity to switch. So these are now just direct time traces of this parity sequence. So you can see we get this telegraph-like signal. That's essentially what we're talking about a while back, of just the string of zeros and ones. And the top ones are when we're injecting very narrow pulses, so not very many phonons, and that's mostly just the background. And then as we turn up the width of our injection pulse, we're injecting more and more photons, the switching gets faster and faster. And so up on the upper right, we're looking at the probability of the qubit parity to switch as a function of sort of the width of the pulse, so the number of phonons we're injecting. And in both cases, it eventually turns up and it'll saturate it at 50%. But you can see for the chip with copper, we have to go to about a 20 times longer pulse. So we have to inject 20 times more phonons to get the same level of poisoning. So we can say that our copper reservoirs are down converting about 95% of these phonons. And sort of in my last two slides here, we're going to talk about just what happens if we don't inject phonons and we just now go slow and we just wait for nature to do its course, gamma rays to randomly bombard the chip. And here we're going to now simultaneously measure these parity signals on all 3 qubits on the chip at the same time. So this is the chip, an example of the trace for the chip with no copper, the control chip. And so we're going to run, in this case, this is just showing just about a minute clip, but we're going to run it for several hours, even tens of hours. Look at the parity switching, and you can see you get these telegraph noise signals, and you can see a lot of single qubit switching, but you can also see places where pairs of qubits are switching their parity at the same time, and even one example where they're all 3 switching together. And we can do that on both chips and analyze the statistics of it. And this is really the last slide. And we can look at then same color scheme. Red is the control chip with no copper. Blue is the chip with the copper for down converting phonons. And the first panel here, we're looking at just single qubit parity switching rates. The middle panel, we're looking at 2-fold coincidences. And the final panel on the right, we're looking at 3-fold coincidences where all 3 qubits switch their parity at the same time. And the takeaway message is the chip with the copper, these correlated parity switching errors are down by like 2 orders of magnitude from the chip that doesn't have the copper on it. Okay, and so this is a big deal potentially for, it got mixed up there, from a standpoint of quantum error correction, where if you think about where you want to be for implementing a fault-tolerant quantum computer, you want your single qubit errors to be as low as possible, but sort of a target in the community is people would like the single qubit errors in your big hundreds or thousands or more qubit processor to be below the 10 to the minus 4 level. But so that means we want the correlated errors between pairs of qubits, not 2 qubit gate errors of 2 qubit entangling gates, but the errors of 2 qubits having an error at the same time. We want that to be less than this squared. Okay, so we want these correlated errors between 2 qubits to be below 10 to the minus 8. And this bar right here represents a 10 to the minus 8 rate if we assume a surface code duty cycle of a megahertz. So we're already better than that. So let me just go ahead and put up my slides here and point you to these 2 papers. This was our paper on the phonon-mediated mechanism that we've talked about for the last part of the talk. This was our preprint that hopefully will be finally published very soon on the photon-mediated poisoning. And I'll stop there and take questions. Yeah.
Are we able to do any trigger constant experiments to actually kind of localize whether.
So that's exactly something we're working on. Probably there's a group at MIT and Will Oliver's group that's probably going to beat us to it. They've been working on this for a year or two now, trying to put some photomultiplier tubes above and below the fridge. But like I said, the muons actually seem to be just based on modeling of sort of the particle impact processes. Muons are a little bit less of a problem than the gammas. And so we're actually just now starting to play around with radioactivity ourselves. So we're this summer planning a series of experiments where we irradiate the chip with gammas in a controllable way. So that's something we're looking forward to, but haven't done it yet.
I'm a little surprised that this wasn't on the radar ahead of time, the gamma ray stuff, because you can take, I mean, low temperature experiments. Like if you take superfluid helium-3 and look at mechanical resonators in helium-3, you can get you can see radiation effects, and the people have seen radiation effects in just semiconductor processors.
Sure, or even hard drives, right? Magnetic hard drives getting
Yeah.
occasional bit flips from, yeah. So it's a good question, and it turns out it's not actually a problem even right now. What I'm talking about, and I should have gone through some of the numbers, but I guess I was rushing a little bit. It's going to be a problem in the next couple of years. So at the current size of qubit chips and the current good but not so great coherence of the qubits means that you can actually live with this at the moment. So for a typical sort of 8mm, centimeter size chip, like our experiment, the Madison experiment, the Google experiment, the impact rate of these gammas or muons hitting the chip is about once every 10 seconds or so. So once every 10 seconds, you have this system-wide scrambling where, okay, most or all of your qubits have a suddenly really bad T1, but the recovery time is pretty fast. Like in our case, it was 60 microseconds. In the Madison experiment, they did a little earlier, it was 130 microseconds. The Google experiment, for reasons we've never fully understood, but they've never totally answered our questions, is up more like 10 milliseconds. But it's still, any of those times are still really fast compared to the 10-second period in between the impacts. So every 10 seconds you have this sudden, the whole chip goes dark and gets really bad. But then it recovers in sort of 100 microseconds up to 10 milliseconds. And then nothing happens until 10 seconds later. Okay, on average, another event happens. Qubit coherences are, the best ones are in the hundreds of microsecond range. So nobody's trying to run at the moment an algorithm that goes out anywhere near 10 seconds. So the odds of having one of these impacts during your computation are relatively small. And if it does happen, okay, you just throw that sequence out and do it over again. But as people work towards bigger processors, the chips have to get bigger. And so it's a constant flux of the gammas or the muons or whatever. So that 10 seconds is going to start to come down to a second or 100 milliseconds. So that rate is going to increase. At the same time, we hope there'll continue to be these advances in coherence of the qubits so that we're going to be running our computations longer and longer. So there's going to be a point, maybe optimistically, in the next couple of years where those two are really going to collide. And these are going to start happening frequently enough that you really care about them. And so this strategy of putting the phonon down conversion on the backside seems to be one path forward to make the qubits be able to live in an environment where they're getting hit periodically with high energy particles.
Maybe time for one more question and then we'll do the lunch. Quick one, go ahead.
Have you noticed putting the copper on the backside decreases the overall T1? So it looks like the copper does a great job of killing the phonons, but kind of similarly to when we were saying if you make the antenna modes higher frequency, you lose because of that electric loss.
Yep.
Have you seen that you lose here because you put normal metal much closer to the qubit?
Yep, it's a good question. So there's actually two things you can worry about. One is, first, if you put just a solid sheet of metal on the backside of the chip, whether or not it's a normal metal or a superconductor, that's a problem. And that's the origin of why we slice this copper layer up into islands. And the problem is you form now a waveguide between the top metal surface ground plane of the chip and this metal on the bottom side that can radiate along with the silicon as a dielectric. And the qubit is going to have, the qubit is some LC oscillator at 5 gigahertz. It can couple to those and radiate away its energy into that waveguide mode. So that can limit T1. So the way to deal with that is to chop that layer in the backside up into little squares that are of order the size of the qubit, which kills that transmission line mode. So you've taken that away. And now the next thing you might wonder about is, I think what your question was, what about just metallic losses, say from the fact that the qubit it's on the opposite side of the chip, but it's not infinitely far away. So there can be some very weak capacitive coupling between the qubit capacitance and this patch of normal metal on the backside. In John Martinez's theory paper from just 2 years ago, he estimated that this would limit the qubit queues to around, I think it was around 1 or 2 million. And for us, our qubits are actually a little bit smaller footprint than in John's calculation. So it would be even a little bit higher. So it's not infinite, but it is a limitation when you start to maybe get beyond 100 microseconds. So T1, you do have to start worrying about it. But there's a relatively easy fix. There's two easy fixes, well, potentially easy fixes. One is that when we make the copper here, we actually already have to put a thin adhesion promotion layer, which we use titanium, because copper on its own doesn't want to stick very well to silicon. So you put a thin titanium layer in between. And it turns out, of course, titanium is a superconductor at very low temperatures, depending on which phase you're talking about. Our titanium layer right now is probably too thin to be going superconducting. But if we made it a little bit thicker, say 100 nanometers, it would be able to go superconducting on its own and then screen out those metallic losses. Another alternative is just to use a low gap superconductor. So it's not clear using a normal metal is the right way to go, because all that you need to do is down convert the phonons to an energy lower than the superconducting gap of the qubits that they're made out of. And so you could use even just titanium by itself is one scenario. Thanks.
Okay, let's thank Britton for the talk.